Hello, okay. So this is the third installment of the project. So I wanted to show how multiplication is a repeated process. How instead of using the multiples and just like knowing it off the top of our head, all the multiples of six, how we can just add six plus six and so on and so forth to get our desired number. Um, so what I mean by that is we can do six, and if we count it one time, we get six. If we count six two separate or two times, we do it like just six uh, plus another six, two, we get 12. We could do plus another six and get three, which would be 18. We could do plus another six, and we get 24. And so Um, with that being said, I've set up this problem of triple digit number times a single digit number, six, and I made this little chart so that we could reference it as we do the intermediate method of multiplication here. So we're going to do just 6 times 2 to start off with. 6 times 2, we count 6 twice, we get 12. So I can just drop that 12 right down. 6 times 3 is our next one. But because the 3 is in the 10 spot, this is actually going to look a little more like 6 times 30 instead. And that's because we have to make sure we're keeping our place values. And by making it 30 instead of just 3, we keep that 3 in the tens place value. So in order to show that, I'll drop a 0 down, and then I'll do 6 times the 3. I just reference my chart up here is 80. Should give me 180. Then we can do 6 times 4, but our 4 is in the 100 spot, so really it's 6 times 400. Since these two are going to be 0, we have to account for, them being. We have to account for the factor being in that place value. So I'm gonna add 2 zeros, and then we'll just count 6 4 times, which is gonna get us 24. Now, this is just a simple addition problem. 2 times plus 0 plus 0, 2. That's gonna be 9. 4 plus 1 is 5, and just drop down the 2. So it's going to give us our answer of 2,592. So next I want to do this equation, which is a whole number times a fraction. And in order to do this correctly, we're going to have to make our whole number a fraction. And in order to make whole numbers fractions, it's pretty simple. All we have to do is put it over 1, because 1 goes into 4 times. It just makes it 4. Um, and then, so let's just go ahead and drop that down into our next fraction. Now we see we have a denominator with a denominator and a numerator with a numerator, whereas we wouldn't have been able to multiply this because we didn't have, it didn't look the same, so it wasn't going to translate. So instead, we have to make it our whole number a fraction. So by doing that, what we can do is then for, well, kind of do this. Now our equation looks like this, and because this is not a addition or subtraction, we don't have to keep the bottom number. We don't have to get the same common denominator. So we're just going to multiply both denominators and numerators in across, going all the way across. And so I can do that. If I count 4 one time, well, I just count it once, it's 4. And I count 1 6 times, I'm gonna get 1, 2, 3, 4, 5, 6. Then we're gonna get this number, 4/6. But we can simplify that because 2 goes into both of these. And 2, 4, 6, 8. Well, I counted 2 twice to get 4. So I could put a 2 there. And to get 2 into 6, or to get 2 to be 6, I have to count it 3 times. So I have to count 2 plus another 2 plus another 2. So I can simplify it and show that it's just a repeated addition process of just not only here, but going like this way, but I'll show you also this. If our number here would have been, let's do 3. If our number here would have been 3 in the denominator, then I would have had to count 3 6 times, or 6 3 times, to get this number here at the bottom. Our original problem didn't have us do that, so we didn't have to, but we can do 3 times 6, count 6 once, 6 plus another 6 is 12, plus another 6 is 18. We do that, and then we could simplify it, so on and so forth if need be. But our original problem didn't have us do that, so I kind of just leave it like that for the time being. So for our next problem, we have to do a whole number times a mixed number. And in order to do this, because they look completely different, this has a fraction, this doesn't, we need to make both of these fractions. We need to make this an improper fraction, and we just need to make this just a fraction. And so we know that if we have a whole number, we need to make it a fraction. We can just put it over 1. So we'll go ahead and we can just drop that 5 down, put it over 1. But now we need to make this a mixed number. So in order to make it a mixed number, we're going to multiply the whole number and the denominator. Then we're going to use that number, and we're going to add the numerator to it. But I get here, and I don't really know what 5 plus 5, or 5 times 5 is, so I can just count 5 times. I can do 5 plus another 5 is 10, plus another 5 is 15, plus another 5 is 20, plus another 5 is 25. Oh, I counted 5 times, so 1, 2, 3, 4, 5. Yeah, counted it 5 times, so our number is going to be 25. So 5 times 5 is going to be 25. And now I'm going to add the numerator, like we said earlier, plus 2 to make 27. And we can drop that down right in there. And then for the denominator here, we're just going to drop the same number down here, because there's no need to change it because it was already a fraction. We just needed to make it an improper fraction by adding all of these whole numbers up to the top. And now that I'm here, my equation now reads 5 times 27 and 1 times 5. But I don't want to count 5 27 times. So in order to simplify it and make it a little quicker, I can see that this 5 and this 5 are common numbers, and that if we wanted, 5 goes into 5 one time. So I could cross that out and make these 1. So now I don't have to count 27 5 times. I can just count it once and get the same answer. So 1 times 27 is 27, and 1, if we count it one time, is 1. Now, this looks an awful lot like 5 over 1, which we used to make 5 a fraction. We had to put it over 1. 27 looks exactly the same over 1. So in order to make this just a whole number, I can just drop my uh, line and my 1 to have 27, and that's my answer. All right, for our final problem of this, we're going to do a decimal times a whole number. And to start this off, this decimal kind of confuses me. It being right here just kind of throws my whole problem off, and it looks really foreign and very weird. So, in order to kind of make it look like a regular math problem, like a regular multiplication problem, I can just move the decimal out of the way for now, and then once I get my equation, I'll move it back in. So, we're going to move it 1, 2, and now, by putting it over here, all I have now is 24 times 3, because we know our decimal separates our whole numbers from the fractions or the smaller numbers after the decimal. So by moving the decimal 2 to the left, let me just make a little note that we moved it 2 to the left. Now I just have kind of a regular problem here. Now I can just do 24 times 3. Well, I know there's 3. If I count it twice, that's 6. If I count 3 another time, that's 9. If I count it one more time, that's 12. All right, so 3 times 4 is 12. Then I am going to do 3, just like our regular multiplication problem from the first problem. We're going to pretend that this is a 0 because the 2 is in the 10 spot. We have to account for that 0. Let's drop that 0 down. And now we will do 6. That's 6. If I count 3 2 times, it's going to be 6. So boom. Now we just have this regular multiplication or addition problem of 72. But now we have to remember we moved the decimal out to the right 2 times. So in order to make this correct, we have to move the decimal back into our problem. And so to do that, our decimal would be here. We're going to just move it 1 and 2. We'll move it right back to the original spot that it was. And it's going to give us our answer of 0.70, 72 hundredths. Because if I move my decimal to the left or to the right, I have to move it back to the left at the end of the equation.